Hello students, welcome back. We completed up to section 2. Now let's go to section 3, quotient fields. And this is very similar to the construction of the rational numbers from integers using appropriate equivalence relation, which we discussed way back in week 1. Let D be an integral domain and define a relation on d times dx as follows. So the first coordinate can be any element of the integral domain, but the second element must be non-zero. Okay? This is not just d times d, but d times dx, so non-zero element. Basically, we're going to set up a over b, so denominator is non-zero. That's what we want. But we do not have division yet, so we define an equivalence relation using multiplication like this. AD is equal to BC. And you can prove that this is an equivalence relation. You can prove the reflexivity, symmetry, and transitivity. Therefore, we can have the equivalent class, and then we can consider as a set of all equivalence classes, which we call the quotient set. And here is an equivalence class. Set of all pairs x comma y that is equivalent to a comma b based upon this equivalence relation. Or in other words, AD is equal to BC, but I replace x comma y in place of c and d. So AY is equal to BX. And then we name it as A over B. In case of integers, 2 over 4 is same as 4 over 8, and that's the same as 12 over 24, and that's same as negative 8 over negative 16, and so on and so forth. Yeah, okay, reflexivity, symmetry, transitivity, and the detail is left to the students. So they are all simple proofs, maybe tedious, but simple proofs that this is an equivalence relation. Now, once you have an equivalence relation, we have the set of all equivalence classes, which we call the quotient set. And then the quotient set can be represented through appropriate representative. And then instead of using traditional expression, a comma b and some bracket or something, I'm writing as a over b expression. And then we define the quotient set like this, yes. And then we can induce the algebraic operation from that of D through this. So arbitrary element in this quotient set is a fraction, A over B plus C over D as AD plus BC over BD like this. You know, usual addition, just as we do this in set of rational numbers. And AB times CD is AC over BD like this. And what we need to do is to prove that these operations are well defined. In other words, if I find different representative for different representatives and then get different expression, but in terms of equivalent classes, they should be the same. And let's see, do we have the proof? Yeah, okay, the elementary but tedious. For the addition, yeah, let's suppose we have two representatives, A1 over B1 is equal to A2 over B2. In other words, those are equivalent. So A comma B and A1 comma B1 and A2 comma B2 are equivalent, like this. And then same for C1 over D1, C2 over D2. And then same for this and that. And okay, all right. All the computations here are elementary, but just tedious. So I'll just leave you there. If you have some time to burn, work those out. And same for multiplication. Yeah, all these computations, those are correct, but tedious. They're elementary. They're all elementary, but they're tedious. So, we do that, and then we end it up with a fraction. And that way we get a field. And this field is called a quotient field. So this thing is called quotient set, but if you induce the algebraic operation from previous structure, integral domain D, this one and that one, addition and multiplication, and then it turns out that it satisfies all those properties of the integral domain, and then this construction, the fraction construction, yielded the multiplicative inverse as well, so we end up with a field. Particularly important case for us is the quotient field of polynomial rings. What do you get? A polynomial, if another polynomial, we end up with rational expressions. And zx with bracket, that's polynomial. Zx with parentheses, that's a rational expression. Qx with bracket, that's polynomial. Qx with parentheses, that's rational. So polynomial over polynomial is a fraction expression. And then Rx, again Rx with parentheses. Those are just notations. So, except for all those tedious steps, we did complete everything. Consequently, we ended up with field of quotients. And for polynomials, basically we ended up constructing rational expressions. Some people call those rational functions. That's okay with me.